Good morning, good afternoon, and good evening, depending on where you're joining us from today, and welcome. My name is Diane Bégin. I'm the Director of Communications at Weizmann Canada. We're very pleased to have over 130 registrants from across Canada and around the world for today's special presentation titled Frontiers of the Universe: How Activities in Space Impact Our Everyday Lives on Earth. For those of you unfamiliar with Weitzman, the Institute has an over 70-year history at the forefront of scientific discovery. Since 1964, Weizmann Canada has been helping to support these critical discoveries. Part of Weitzman's reputation is built by challenging current thinking, which has led to life-changing breakthroughs. Recently, Weitzman ranked 8th in the world for research quality in the prestigious Leiden University ranking, the only non-American institute to rank in the top 8 among the likes of Harvard, Princeton, and MIT. One thing the current pandemic has taught us is that science is the key to a better tomorrow for all of humanity, because science really knows no borders. By transcending borders, Weitzman research also reaches us in Canada every single day. Since 2019, Weitzman has co-published over 80 studies with more than 30 Canadian organizations. Encouraging dialogue and collaboration to promote new discoveries is what Weitzman is all about, which is why we're so very pleased to welcome you here today. Before we get into the panel discussion, just a few housekeeping points. We'll begin with a brief introduction from each of our panelists, describing their respective areas of work, followed by a panel discussion. In that time, I encourage all of you to type questions into the chat box for this webinar. We'll come back to your questions in the latter part of this panel discussion when we open it up to an audience Q&A. We promise to finish up within the hour so that you can carry on with the rest of your days. If you are interested in learning more about Weitzman following this event, please reach out to my colleague, Anna Katsouforis, at anna@weitzman.ca. The topic of how activities in space impact our everyday lives on Earth involves a discussion about physics, from the incredibly tiny in particle physics to the immensity of astrophysics, which is why these two areas need one another and why our esteemed panelists are here today to talk exactly about that. Today's event is under the banner of our Women for Science initiative, featuring the incredible work of global scientific leaders. We're in for a fascinating discussion ahead of us. Now, instead of reading their bios, we've asked each of the panelists to let us know 3 accomplishments that each is proud of as they relate to today's presentations. So let's get started. Professor Victoria Kaspi is a professor of physics and director of the McGill Space Institute at McGill University. Now, when it comes to her 3 accomplishments, here's what Victoria said. Discovered that a puzzling class of X-ray emitting stars are magnetars, the most highly magnetized stars in the known universe. Is presently trying to understand the mysterious class of astrophysical objects called fast radio bursts. Founded and is the inaugural director of the McGill Space Institute, an interdisciplinary research institute that brings together researchers with diverse space-related interests. Professor Kaspi is the mother of 3 and also has a long history with Weitzman, having started her science career, so to speak, as a young student in the International Summer Science Institute, also known as ISSI. Fortunately for us at Weizmann Canada, we've also benefited from Professor Kaspi's deep expertise for many years as a volunteer advisor, including a leadership role in judging the annual physics competition here in Canada. Incidentally, the International Physics Competition took place earlier today. We were represented this year by 4 Canadian teams. The tournament involves student teams that take on a challenge to build a safe that only their team can open, and then they try to open safes from all the other teams. So big congratulations to this year's winning team from the UK and to all participants from around the world. If you'd like to learn more about these educational programs and so many more, please go to weitzman.ca/educational-programs. The link will also be provided in the chat. So ISSI, that I mentioned earlier, is also a program of the Weitzman's Davidson Institute of Science Education, where our next panelist works. So Dr. Namashari Yari is the head of innovation initiatives in science education at Weizmann's Davidson Institute. Naama's accomplishments as they relate to today's presentation include a mother of 7 children, all now grown, so 6 boys and 1 girl. When she's wearing her education hat, it is leading the educational arm at Weitzmann that we call the Davidson Institute. And when she's wearing her research hat, working with the United Nations Comprehensive Nuclear Test Ban Treaty Organization to ban nuclear explosions by everyone everywhere. Now, she was the only woman nuclear inspector for many years. And in Naama's own words, now there are a few more women, but it's still very male-dominated. A bonus fact about Naama, she also goes trekking in the mountains in her spare time to help re-energize herself. And then our final panelist is Dr. Shikma Bressler, head of the Kushner Family Particle Detector Lab at Weitzmann. Shikma's accomplishments as they relate to today's presentation include raising 5 daughters, and in Shikma's own words, it's of course the best. Leading the Israeli effort to upgrade the Atlas detectors, the largest general purpose particle detector experiment at CERN in Switzerland. She adds, I'm proud of the fact that we're doing it as a team. And finally, her third accomplishment as it relates to today's presentation, taking a leading role in educating the next generation of academics through what I hope will become cutting-edge science. Ladies and gentlemen, please welcome Professor Victoria Kaspi, Dr. Namashari Yari, and Dr. Shikma Bressler. Welcome, ladies. So to get us started, we will turn over to Naama. And I am going to ask you to explain what you do. But before we do that, can you start, Naama, by explaining what astrophysics is, what particle physics is, and the intersection of the two?
So just to sum it into one sentence, when I usually talk, I say that physics, when people think of physicists, they think of particle physics. I mean, physics that deals with the very, very small numbers, or astronomy and cosmology that deal with huge numbers. But physics actually deals with everything in the middle, everything in our world. And there's a whole world, a field of research that emerges at the intersection of these fields. It uses infrastructures and methods to detect a wide range of cosmic particles, including neutrinos, gamma rays, cosmic rays, dark matter, gravitational waves. It's a fascinating field, and I'm sure we will see that today. So what I do is I'm actually a nuclear inspector for the United Nations Comprehensive Nuclear Test Ban Treaty Organization. My work for the past 25 or so years is actually to develop the instrumentation and methods for the detection of isotopes in the environment. Such research can be used, or as I used it, for example, to advance research on early detection of earthquakes or volcanic eruptions, all sorts of geodynamic events. Specifically at the UN, I work on developing the instrumentation and developing the analytical methods that are used to detect radioactive isotopes in the environment, and to be used for detecting use of nuclear weapons. So I develop the methods, I develop the instrumentation, but also I teach those methods to the cadre of nuclear inspectors, all of which are scientists from 186 countries around the world, so that we can fulfill our duties when we're called upon. So this actually ties in with my job, developing science education, innovative programs, and especially engaging young women, young children, even very, very young children, to develop a love for science. There is a known saying that if you choose a job you like, you never have to work a day in your life. So I love science, especially physics, and I love explaining science. So I count myself as being really blessed in being able to merge these two.
I love science too. And thank you, Naama. And it establishes a great foundation for today's discussion. So, Vicki, over to you to explain what you do.
Well, hello, and thank you for having me here. Very excited to be here. I am an astrophysicist. I am in a department of physics, so I'm also a physicist. And that means that I study objects that are in the very distant universe, both inside our own Milky Way galaxy, but also far outside the galaxy. I am an observational astrophysicist, which means that I use telescopes and collect data and analyze it and try and apply the laws of physics that we know from our laboratory experiments here on Earth, the sorts of laboratories, including particle accelerators like Dr. Bressler works with. All the laws of physics we learn on Earth, and we try to apply it to understand very dramatic violence phenomena that we see in the sky at cosmic distances. And right now, what my research is involving is trying to study a newly recognized astrophysical puzzle. We see a phenomenon in the sky that we have only recently appreciated, but we don't know what it is. We don't know the origin of it. The observational signature, what we see are very brief flashes of radio waves coming from very far outside our own galaxy, indeed at the furthest reaches of the universe, billions of light years away. We don't know what's causing them. And but they last only a few thousandths of a second. So just brief flash and then it's gone. And we're trying to understand what these things are. We know that if we can observe them on Earth from so far away, they must be incredibly bright and extremely energetic. And somehow nature has found a way to create what must be a titanic explosion. And we don't know how that's working. We think that's an important thing to understand. And that's what I'm presently working on.
Fascinating. And I love that in terms of we don't know what we don't know, right? And that's what science is about. And that's what exploration is about. So, Shikma, over to you.
So, by definition, I'm a particle physicist, which means that we are trying to investigate and understand and study what you would call or refer to as the fundamental building blocks of the universe. What would you see or artificially see if you just cut everything into pieces and then take the smaller piece and cut it again and take it and cut it again and cut it again and do it one time after the other? So we are looking at things which hopefully, or by the theory that we are working with, has actually no size at all. So in the framework that we are working on, the way that we interpret what we see, everything is made of these fundamental building blocks, and there is basically nothing in between them. So in this respect, if we could just, so what we actually see in the universe is just the interaction of those particles with each other. So according to the way that we understand nature, and by understanding I mean that we have some mathematical formulas that we can write and try to deduce what will be measured out of this formula. According to this formula, what we get is that if you have enough power to even squeeze the entire universe, we will actually get, a handful of nothing, because everything is made of particles which has no sizes at all. So this is what we are after. What are those particles which are sizeless, actually? How they interact with each other. We have a very nice understanding of that so far, but it's already clear that the things that we understand, we are missing a lot of understanding. Because if we look out, for instance, at the universe, and we do the relevant measurement and calculation, what you will find out is that we only understand by our theories less than 5% of the entire mass that we see around us. So it's clear for us that there are things that we are missing. We have no idea what it is, what it might look like. And this is, I think, what I'm mostly driven by, to find a hint of what these things that we have no clue what they are, but we know that it should be there. try to find a clue, a handle that will take us forward. In this respect, we need to develop our instrumentation as well. So I work on that as well, trying to understand what might be our blind spots in the ways that we are analyzing the data on one hand, or measure it on the other hand, and try to build future instrumentation. And then it turns out that when you develop cutting-edge technologies to answer cutting-edge scientific questions, there are a lot of byproducts which are amazing, right? So we have in my lab, we develop detectors that are nowadays used to try to build systems to identify radioactive nuclear materials which are going back and forth without us knowing about them illegally. And we contribute a lot by understanding how those particles may interact to fields like hadron therapy, which is now emerging with all these using protons and hadrons, other particles, to try to cure cancer and so on. And I find it amazing that when as a scientist, I'm inspired by the scientific question. This is what drives me. But because of that, because we don't, in principle, think of the outcomes, what you get is so unexpected and so broaden the ways that we can, the things that we can do. So this is what I'm doing and why I like it.
And that's really interesting, because you mentioned, we can't be thinking about the outcomes because we don't know what we don't know. And a stat that you mentioned in your introduction, Shikma, was that we know about 5% of the known universe at this point, which leaves a pretty huge blind spot with 95% that we actually don't know about. So just to build on that, why does everything from particle physics to astrophysics matter to solve earthly problems?
Yes. Why does it matters? I think, well, again, we actually, I heard a presentation today about Aristotle, who said that the essence of human being is just, not to ask why does things matter, but, just try to understand what it is. So I think that we want to understand what it is because we see it. I think that from, dawn on humanity, people ask, what does the universe made of? So they started by saying it was, earth, wind, water, and fire. And now we are just continue pursuing this particular track. And this is extremely important, because imagine what would have happened if we just continue thinking that the world is made of earth, wind, fire, and water. And when we continue beyond that and we discover the elements, for instance, imagine what would we have without the table of elements today. So being continuously walking along this path, we have no idea what we will imagine, but history tells us what we'll be discovering. But history tells us that we will be discovering, we may be discovering, we have a great potential of discovering something that will take us forward. And as I said, by doing that, we're already contributing in so many other manners that I don't want to stop walking along this path, right?
And one of those things that you mentioned, Shikma, earlier was even with cancer treatments, for example. So Naama, over to you now. Why does everything from particle physics to astrophysics matter to solve earthly problems?
So I think that science is behind innovation in almost every field. So we live in a technology, in a science-based world. Almost every decision we make in our daily lives relies in some aspect on science and technology. And we may think that science has only taken us to the moon, maybe cured disease, but every decision we do, every simple decision even, relies on science. So I think it's important to us to speak, to all of us, to speak the language or the basics of this language of science, and to be a part of, so that we are a part of the society's decision-making, based on knowledge, not just based on belief. And I also think that science and technology has given us the gift of time. So sometimes it feels like when I talk to people that we have no time in the modern world. But I think it's actually not true. It's just that we found new ways to fill our time with. We are surrounded by science and technology in our daily lives, and it saves us time and it frees our time to do other things. And though it might seem like science and technology causes problems and complicates things, and that some people say that they yearn for a simpler life, the truth is that science and technology have solved society's problem and will surely continue to do so in the future. And the path to solve these problems is not straightforward, like Shikma says. It's you research one thing and you advance another field. So.
And so interesting, Naama, because you also mentioned we all have this role. I'm not a scientist, but we all have this role to understand and appreciate science because it impacts all of us. Yeah. Vicky, over to you. Now, why does it matter?
Well, I think I would just be amplifying what both Shikma and Naama said, but maybe I would elaborate a little bit on that. So, if you think maybe 100, 150 years ago, how you might have wanted to address the problem of it getting dark early and wanting to be able to extend working hours, you might have invested, if you were government, you might have invested research dollars in developing more efficient candle wax and better wicks for those candles so they could burn longer to have more light. And of course, you would have had no idea of the revolution that was to come, electricity, where nobody envisioned that and how it would impact our lives, and that now you can, FaceTime with someone around the world with your phone. And how did that come about? That came about with someone playing with a kite during a lightning storm just because they were curious about how that worked. Or it came about with someone sitting and playing with magnets and understanding how moving magnets affect currents and piecing out the laws of electricity and magnetism. And so, we think of some of the sorts of science that people do as being kind of esoteric and not necessarily having immediate impact, but it has potential for massive transformative impact in the long run. So, I think of, in astrophysics, when we're trying to develop, I can speak from my own experience when we're trying to answer a question like, what are these short millisecond, thousandth of a second bursts of radio waves? That's a crazy question. How could that impact somebody here? But we attack it using technology, and technology that doesn't necessarily exist. We have to develop technology. How do you study something when you can't predict where and when it will occur on the sky? You need a telescope that can see everywhere all the time. That seems technologically impossible, but we have developed a telescope here in Canada called the telescope, which does exactly that, and it pushes forward the frontier of telecommunications, antennas. We need massive supercomputers. We need sophisticated algorithms. We need big data management and big data visualization, and all of this is highly transferable to industry and to how increasingly our computer dominated society functions. And we're developing techniques that will radically change in the future how people's lives will work. So it sometimes science seems very esoteric, but by pushing forward the frontier, by asking very bold questions that seem impossible to answer, technology gets pushed forward as well.
And I find this fascinating because my next question might be a little bit impossible to answer, but I am going to put it out there. So if we all kind of dream forward 5, 10, 15 years from now, what do you hope that particle physics and astrophysics will uncover? And maybe Naama, let's begin with you.
I'll begin with the educational part, actually, because the dream forward for me would be to have more capable youngsters grow up to be capable citizens, capable in science. So to have a lot more young women, also young men, but a lot more young women develop a love for science. Maybe some of them pursue a career in science, but even if not, just have an understanding of our science-based technological world, I would want a half of the cadre of the nuclear inspectors to be women, not men-dominated. In terms of research, I think I would like to see a world that invests in nuclear power rather than nuclear weapons, and maybe research and bring fusion finally to a point where we can make electricity with it. So there's a joke about fusion energy. It's about 30 years old, and it says that in 30 years we'll solve this problem. And the joke is that it's always 30 years. We're always 30 years away from having power from nuclear fusion. So it's my hope and maybe a little bit of a wish that results of decades of scientific advancement in this field will bring forward, and we have the means that we will get there maybe in 15 to 20 years. So,
Shikma, over to you. How would you build on that? What would you like to see if you dream forward?
But I hope that we are at the, we might be walking at the verge of a discovery in the sense of, as I said, getting a handle of seeing something unexpected. Unexpected in the sense that as I said, we know that there must be something out there. We have no clue what it is, where it may be hiding, or how it might be hiding. But something should be seen. And if it is within the regimes that we are currently investigating, I certainly hope that we will uncover it. I mean, in Atlas, at the data collected at the huge accelerators at CERN, we have tons, literally tons. We collide particles there, 10 to the 11 protons, over 10 to the 11 protons, 40 million times a second, and we're already doing it for 15 years. So we have a huge amount of data to analyze and try to dig out some, hint for something that we haven't dreamed of. So I think that we should be able to cover better this amount of data that we have and try to reveal something which is new, which hopefully will give us a clue how to build upon the theories that we currently have and go steps forward to new theories and new explanation. And the big dream, I would say, is not just discover something that will answer those questions that we don't have answer to, but that it will lead to new questions that we cannot even imagine at the moment. So it's this is what I hope.
So wading into that data to figure out what those new questions might possibly be.
At the moment, my main, my main focus. What are we missing there? Huge amount of data, tiny signatures that should be somehow digged out. Where are you looking at? If Victoria talked about a telescope that looks everywhere all the time, I need to find something that looks everywhere on a huge amount of data and look for tiny stuff. Where, how? This is what we try to develop. This is the methodologies that we are working on, and I think that we are making steps forward all the time.
Great. Over to you. What do you hope to see?
I think, in terms of the practical side of, how science is done, I'd really hope for increased diversity in science, both certainly gender, but I'd also love to see poorer countries getting involved in the endeavors of science. I feel the world's not quite equitable. It'd be nice to see more racial diversity in science. I think that would be very nice. I'd also like to see the present trend that I perceive toward mistrust of science, concern about the scientific method, people not really understanding how science is done. I would love to see that addressed and improved on, so that we don't have to keep having the same debates about, vaccinations. That's a big issue, and it has life and death consequences for not appreciating how science is accomplished. On the scientific front, in terms of astrophysics, I think in the next 15, 20 years, one of the big frontiers will be the potential for discovery of life outside our solar system, off the planet. In fact, there's been a massive revolution in detection of planets around other stars, around other suns throughout the galaxy. And there's tremendous, particularly since the launch of the James Webb Space Telescope, tremendous potential for not so much, seeing little green people waving at us, not so much that, but more for the detection of signatures of biological processes on planets elsewhere. We call those biosignatures. And I think the next 15 to 20 years has really potential for detection of biosignatures and demonstrating the existence of some form, perhaps just microbial, in fact, most likely microbial life somewhere else. And I think that would be really revolutionary and mind changing, paradigm changing. I would love to see that in 15 years.
Great. And it's interesting, as the three of you were talking as well, over the weekend we were watching Back to the Future, and how we never imagine the future, how it's portrayed in movies. We never have any idea or concept. The year that they fast forwarded to was about 2015, and the world that they created was not the world that we know today. So, I think that's a great metaphor for understanding that we don't know what we don't know. And so how can we know until we actually dive in? So then let's move on to why now? What developments make it important to focus on this area of research right now? Shikma, let's start with you.
Why? Well, because now it's the best time to do everything that you want to do, I think. There is no better time than now for anything, I believe. So, we just discussed so many open questions. We know the potential of improvement of society based on trying to answer those questions. So the answer to the question why now for me is because now is the best time to do whatever you want to do. Never wait. Let's move forward. As simple as that.
As simple as that. The time is now. Naama.
So before I answer, just a short, 20-second story. When I was pregnant with one of the boys, a neighbor of mine, she felt my stomach and said, "Oh, it's a girl." So I told her, "Look, I had an ultrasound, and they said it's a boy." And she looked at me, and said, "And you believe ultrasound?" So I think the COVID pandemic has revealed that a shockingly large fraction of the public is willing to ignore scientific judgments on issues such as vaccines and mask wearing, like Shikma said. And for far too many, scientific findings are viewed as beliefs of scientists rather as the product of a community that uses processes to produce reliable knowledge. And I think this widespread misunderstanding should be a wake-up call for us because it clearly demonstrates that we need to even change the standard way we teach science, not teach it like a large collection of facts that scientists have discovered about the world. I think we need a major change, teach differently, teach the scientific method. So I think first of all that Shikma is right. Now is a very good time for everything. And I think even more so because of the pandemic.
And I think, Naama, you bring an interesting perspective because you also have the education hat in terms of educating youth. So how do you explain that? I mean, I'm sure you've had students throughout this pandemic, they've heard things in their families, with their friends. How do you shift that sort of belief of what science is about? It's not just a set of facts here today. It is that evidence-based approach. How do we shift that?
So I think the answer is always with education. And I think education, by saying education, I mean even talking about cutting edge science, teaching the scientific method rather than the facts. And teaching the enthusiasm that goes with doing science, because I think it is captivating. And so this is, I think, the way to go about it. This is what we're trying to do at the Davidson Institute. Teach everyone from very, very young children. So we're working now on the Chlor Garden of Science, and empowering women, and working with minorities, whether it's minorities from places that are just far away, not in the center of Israel, or not in the center of society. And I think this is the way to do it, slowly, with education. So we need to educate the public to consume science.
And on that note, if you do want to consume science, the Davidson Institute actually has a really great website, and I love consuming that content, asking everyday questions, why is the sky blue? And really breaking down the science. So I highly recommend that as a resource. Vicky, over to you. Why now?
Well, before I answer that, I'm just curious, Naama, was the ultrasound right about your baby?
No, it was another boy.
Oh, wait. Okay. I thought your neighbor said it was a girl, but okay.
Yeah, she said it was a girl, but it was but the ultrasound saw another boy, and it was another boy, of course.
Okay. Yeah. Just checking the ultrasound, of course, is right. So
yay,
good.
Science.
Yes, yay, science. Yeah. So why now? So in addition to the answers that have already been given, I would throw in one more, which is computers. So we are in the midst of a massive revolution. We had industrial revolution a couple hundred years ago. We're in the computer revolution right now, and that is enabling, paradigm shifting changes in the way we do research, the way we look at information, the way we collect information and sift through it and visualize it. I think I can say in astrophysics, a telescope that looks everywhere all the time. This is entirely possible today because of the development of faster computers, and I think that's true in particle physics, and it must be true. The development of artificial intelligence algorithms and machine learning, training machines to do all sorts of amazing feats. And on the horizon is quantum computing, which is going to revolutionize what we already have now, even more so. So I think the time is now for the reasons given, but also because of developments in computing is radically changing the face of science and everyday life.
Maybe if I can just contribute to that, I think that doing science now will also contribute to the way that computers are being built. We are now collaborating with teams from the AI international teams of Intel, for instance. They come to us to understand the problems together. So it goes along. It's not just that we can use the new computers and new computing techniques that are available, but in order to develop tomorrow's computer, they need an input from those people or those fields dealing with, it goes again to the same terminology of cutting edge science. So the contribution is bi-directional in this respect. So yeah, we use a lot computers, but what we learn along that is that the way that the computers are being formed is not exactly suitable for our needs, for the needs of humanity in the future, and then it will result in modifications and probably new ways of doing computers in the future as well.
And that's why we're also talking about quantum computers as well. And incidentally, the Weizmann Institute joined the Quantum Computing Club a few weeks ago with a quantum computer on campus. So really, the systems that we've had in the past, because there is so much data, really trying to mine through all of that and try to make sense of it, and looking at new ways for computing as well. At this time, just a quick reminder to post any questions in the chat, and we will begin with the audience Q&A shortly. Before we get there, though, final question, and I'm going to direct this to Naama and Shikma. Why Weitzman? Maybe Naama, let's start with you. Why is Weitzman a really great place to lead some of these discoveries?
So I think, first of all, I think Weitzman is really special. It's for me, it's very special in the sense that since it was founded, education and research have been going hand in hand. And like so many years ago, it was something that was absent from the academia, but in Weitzmann, it was founded together. So at the Davidson Institute within the Weizmann Institute of Science, we really aim to bring cutting edge science to everyone. So we are talking about children, adults, teachers, everywhere in the world. And we're currently upgrading the Clore Garden of Science, that it will be one of the leading science centers in the world. And our goal is actually to tell the story of science in an interactive, in an engaging way, in a way that is different, as I said, not just stating the facts, but in a way that will be different. Also, as unfortunately there are not enough girls and women that choose to study physics, it is very important to us to expose more girls to the excitement of physics and to have more women physicists in the future. And I think this is why Weitzmann. I think this is what makes Weitzmann very special in this sense.
Great. Shikma, why Weitzmann?
So I think I have actually a good perspective to answer this question. I'm part of the Atlas collaboration, so I meet on a regular basis with people from institutions all over the world, also in Israel. I'm relatively young PI at the institute, so when I joined, we had a meeting with the president, and he was saying that the institute works such that the main goal that they have is to allow us to do the research that we want, to follow our dreams, and they will do everything to assist us with that. And I was, thinking in between myself, yeah, right, they always say that. I mean, they have to say that, right? But this is really the truth, about Weitzmann. Everything at Weitzmann, from the students, administration, everything is just focusing on making. And it's, again, I sometimes I talk and it sounds like, huge cliche, but it's not. They're really working to help you to do the best science, to give you all the opportunities that you have. Sometimes it's even stressful, right? You have no one to blame. It's really on you, because if I want to do something, the institute will allow me to do that. If I really have scientific motivation, it's easy to judge. And besides, if you ever been to the Weitzmann Institute and seen the campus itself, then the question disappears immediately. It's just so beautiful and so friendly.
And the next question, actually, I'm going to open it up to the full panel, and it's something that you've all touched on. So we obviously all have a role in understanding science and science literacy and having conversations every day about science and how it impacts our lives. But let's focus specifically right now on youth. And, if we want to be inspiring more men and women, little boys, little girls, to go into science, what advice would you give them? And maybe, Vicky, let's start with you.
Well, first, so I guess it would depend on what stage youth you mean. I think that the issues in behind why there's such a gender imbalance in science, they start very early. I remember my daughter, when she was in pre-kindergarten, telling me that computers were for boys. And, this is a kid who has a mother who's like glued to her computer. So, where did she get that idea? I don't know. And, but she definitely got it by that age. And so, I think it has to start very early. But probably Naama can correct me, but I know there's, we refer to the path that women take to go from youth to professional careers as a pipeline, but that it's very leaky, so that at each different stage in this pipeline, women choose to leave and so the question is, how can we make science more inclusive? How can we make it something that is clearly for everyone, that is a joy, that needs people with different ideas, different types of creativity, that diversity in science is a true strength, that coming at things from different perspectives and with different styles is actually what is going to push forward science in the most efficient way. So I think that's exactly what the answer to your question is. Depends on where you are. In high school, you need concerted efforts to keep girls interested in pursuing science. You need it at elementary school, and you absolutely need it in universities. And then even beyond that, for faculty members, you need to have, and the issues at each stage are different. Faculty members are worried about childcare. We need to ensure that that's handled properly, that it should not be a stressful thing to want to have both a career and children. But on the other hand, undergraduates, they need encouragement in different ways. So it's a complex question, and there's a variety of different answers depending what stage. But at every stage, there's work to be done.
So we really do need to fix that leaky pipeline, no matter where they are as part of that journey. Shikma, over to you.
I just agree with everything that that has been said. I think that we need to. I mean, occasionally when I talk to people and I introduce myself and I say, look, I'm a physicist, you get immediate this people get I don't understand anything about it. It's the hardest stuff. So this is the first obstacle that we need to somehow remove. It's not about being geniuses and stuff. It's you can do that. Everyone can do that. Maybe not everyone, but also not everyone can can write literature, right? So if and probably a lot more people has the skills to deal with science and to work on science and they appreciate. So we need to somehow get rid of this fear. I think again it goes into education and the way you introduce that. Introducing physics just as complicated calculations, probably doing wrong. I mean, I usually say that, okay, there could be so many examples and ways to explain fundamental laws of physics, of science, which are really a lot more fundamental from what we usually teach at high school. And those things people can understand. I mean, I won't give an example right now, but you can explain extremely deep concept in science in a way that everyone can understand. And then you can by this it's teaching methodologies, but also teaching concepts and let people feel the joy of understanding something which is deep. And there are tons of examples. We just need to find the right way to do it. And I think it will attract people. When people will be less afraid of stuff, they immediately approach it, right?
Yeah, and I guess it comes back to the whole idea that we don't know what we don't know. So if somebody's not exposed to something, how do they know they're actually going to like it? And so we need to reframe those conversations. Absolutely. Naama, over to you. How would you get younger people interested?
I really agree with what Vicky and Shikma said. I think we should start with science is fun, and then as kids get older, show them that science is like the study of the natural world in a systematic way. And it sometimes it is hard work, but it's worth it. You do enjoy the work. You do enjoy the process, and the process is the most important thing in science. So I think this is the way to approach it. Yeah, how not? I love Vicky's this, adjective of a leaky pipeline. It's I think it's brilliant. I think this is what we have because girls, even in university, I mean, even there are maybe less girls that study physics, but when we get to higher degrees, sometimes there is almost half. But then when we get to faculty members, we lose them in the way. And I think we have to start when they're young and maybe for a generation to go along with those, so that we don't lose them, so that we have more women in faculty, we have more diversity, and surely the scientific method will only benefit from that. So
can also add that Weitzman is engaged with that right now. I mean, there is a lot of activity in this direction at Weitzman Institute. We even have a particle physicist, which study part-time sociological aspects of diversity and women in science. So all these pipeline issues, these things are now being studied more systematically in the context, in particular, of physics. So there will be more data on that in the future. And here again, my physicist approach is pumping in. There will be more data. We will be able to do something based on concrete knowledge. Also, in this respect, there should be answers lying out there somewhere.
And hopefully we'll also have the platform to engage them from when they're very young, even like 3-4-year-olds at the Clore Garden of Science, and then through the Davidson Institute until they're students, and maybe even afterwards. I know that teachers use a lot our website, the Davidson Institute website, to download information and to get scientific help on issues they feel they need help with. So yeah, I agree with Shikma. I hope we'll get there.
Great. And so then let's shift gears a little bit, and I'm not sure who might be interested in taking this on, but how will Ultrasat aid in discovery, problem solving, and innovation? And maybe starting off a little bit by explaining Ultrasat. Naama, is that something you're comfortable taking on?
Yeah, Ultrasat is a telescope, mostly based on Israeli technology, except the camera that's German, but the screen is Israeli. So it's Israeli technology at its best. It's going to be a very unique telescope because it's going to look on the ultrasound part of the spectrum. It's going to see a very wide angle of the sky, wider than has been done up to now. And so it's going to be able to detect what we call violent, the English word I'm missing, but violent
transient.
Transient. Yeah. And it's going to be able to, and it's going to be sort of like a lighthouse. So it's going to be able to see it in the world. It's going to be able to give to show that it has seen it in like 15 minutes, and so that other telescopes can, and all over the world, can continue and watch this event. And it's going to look at very short astrophysical events. So probably Vicky can elaborate more on that.
Vicky.
Yeah, sure. Yeah, so we, one of the big revolutions in astrophysics, computer enabled in the past decade, is recognizing that the sky is filled with events, massive explosions that come and go and disappear, and to try and understand those powerful energetic events, we need, like I said before, and is relevant to Ultrasat, telescopes that can see large areas of the sky at once, rather than just focusing on one tiny little region of the sky. So with a conventional telescope, you look in one direction and there's something way over here going off and you don't see it. You have no clue. Here with Ultrasat, which is which is going to be sensitive in the ultraviolet portion of the spectrum, so our eyes can see just the optical, very, very narrow range of the full spectrum of the types of light that we have. The CHIME telescope that McGill and other universities in Canada has built can see in the radio portion of the spectrum. There's telescopes that can see in the X-ray portion of the spectrum. So Ultrasat will be in the ultraviolet portion, which is a really unique area. I think Ultrasat is going to be truly unique of the missions flying a satellite mission, because you want to have it in orbit and able to see large areas, and then to compare what they see with what is seen at the other types of light. So I would really look forward to working with Ultrasat, to combining Ultrasat data with CHIME data, for example, to get two very complementary different views of the same sky, to help us understand what these enormous explosions from where they originate.
And we could go on, I'm sure, but we're almost at the hour. So I wanted to thank you, ladies, for your time. I think this was a fascinating discussion. I definitely learned quite a bit, actually, and am excited to have the conversation continue. So at this time, I would like to thank you all in our audience as well for joining us today. Before I turn over the microphone, I wanted to mention, should you wish to donate to Weizmann Canada to support the vital scientific research that leads to discovery that we talked about today, you'll find a donate button on this webinar window, and there will also be a link in the email that will include the recording of this event. I will now turn it over to Susan Stern, National Executive Director and CEO, to say a few final words. Thank you.
Thanks to our panelists for taking time to be with us and for sharing such exciting research and insights with us. Thank you, Diane, for expertly moderating the discussion. It was fascinating. I'm sure the conversation could go on for hours. And as Diane said, a special thank you goes to all of you for choosing to spend the last 60 minutes with us, and a lot of great questions, and feel free to continue to ask those questions and we'll get them answered for you. We look forward to continuing the conversation with you. I'm sure we all have some great takeaways from the panel, which provides some new food for thought when it comes to why advancements in space research matter to us here on Earth. I hope that your dinner table conversation this evening will include things like the ability to detect nuclear activity, the meaning of dark matter, the role of physics in a potential cure for cancer, life outside our planet, the leaky pipeline, and most importantly, how important it is to be curious. I'll leave you with Diane's question to explore. Why is the sky blue? Have fun with that one. As you heard at the beginning of the event, the Weitzman campus is characterized by the joy and pursuit of science. There's a multidisciplinary approach and an openness to share knowledge and embrace new ideas. The Weitzman model enables scientists to be curious and offer the freedom for boundless creativity, and also encourages global collaboration, including the many you heard about earlier. We've all been subject to a very long science lesson over the last 2 years. And although many people have learned the importance of basic science, as you heard from our panelists, it's now up to all of us to help encourage science and talk about science. We invest in discovery, recognizing that with time, space, and resources, the scientists put hope in action and make a global impact. And now that things are starting to open up a little bit again, if you're traveling and you're interested in visiting the incredible campus at the Weitzman Institute, please reach out to Anna, who's the Director of Events and Experiences, at anna@weitzman.ca. Her email address was also included in the confirmation. Please follow us on your favorite social media platform to learn more about research and discoveries and upcoming events. And thank you all once again for joining us. Have a wonderful rest of the day. Stay safe, stay happy, stay curious.